Hi, everybody. We'll get started here in about 2 to 3 minutes. Thanks for your patience. All right, everybody. Thanks for joining in this afternoon. Let me ask before I share my screen. First, let me say the reminder we're being recorded. So I will share a copy of this recording in the announcements in a day or so once I get it captioned. So before I go ahead and share my screen, let me just ask if there are any questions out there. If you need to ask a question about anything, just type it in the chat or unmute and feel free to ask your question. Okay, well, I didn't get any takers on that, so that tells me that everybody's good. Let me go ahead and share my screen. So will somebody kindly just
there's this. Because it's fun. It's not what you want. You know where I am. Second.
Sorry, everybody. I dropped my signal dropped for a moment. I do apologize about that. Let me go ahead and share my screen again. There we go. Okay. All right. Please let me know if you're seeing my screen now. Somebody?
Yes, ma'am.
Thank you very much. Okay. So just as a reminder, I'll be posting the this video in the announcements once we're done. Let me make sure that it is recording. Yeah. Okay. So let's jump right into weekly overviews. And last week I did tell you that this week we will begin looking at the summary that you have to write. So I'm gonna go into the project details. Okay. So today I want to give you the basics of the summary that you have to write, because you had until this past Saturday to find a research article, send it to me and get it approved. And it tells you in the directions here, if you did not get an article approved, you can still do the project, but you, at this point, you will be working with an article that does not have my approval. So you would lose 20 points from your score. There's a category in the rubric that's included in the project folder. And there's a category in that rubric that says article choice. If you got your article approved, then you automatically, well, if you got your article approved and you summarize that article, then you get those 20 points. If you did not get an article approved, you lost those 20 points in the article choice category. You can still do the project, because you see that bolded there, you can still do the project, but if you are working with an article that is not approved, and it turns out that the article does not meet the standards, meaning it's too short, it is not on a proper topic, or it's not peer reviewed. So if your article that is not approved, that you use to do the project, does not meet the standards, then you automatically get a 0 on the project. Because in essence, if you didn't get an article approved and you do the project, you're taking a chance, because you really don't know if that article is acceptable. So for those people who got their article approved, you don't have that to worry about, as long as you do a proper summary beyond the article, getting your article approved, okay? Does everybody understand that? Because if you send me an article at this point for approval, I'm going to tell you I'm no longer accepting, reviewing, or approving articles. Please consult the project details for additional information, okay? Because you had, you know, a good chunk of time to send that to me, all right? So you got, let's say you got your article approved, you're reading it, and at some point you're going to move beyond reading the article to begin summarizing the article. So the summary that you have to write has to be a minimum of 2 pages in length, typed, double spaced, in a 12-point font, okay? And I give you your first sentence. I am summarizing the article name, fill in the blank, written by, fill in the blank, published in the year, fill in the blank. Okay, so that is how you should start the actual body of your summary. The first, that's how you should start. That should be the first sentence in your actual summary. But there's some other things that you have to do before you actually write that first sentence. And that is, you need to make sure that your paper, it has a 1-inch margin all around. Okay, 1-inch margin all around. That's proper APA format. APA, the American Psychological Association. They're the ones that set the standards for scientific publications. And so 1-inch margin all around, double spacing. Now, there are certain things that are APA format that you don't have to do. Okay, the margins and the spacing you do have to do, but you do not need an abstract. If you look at sample papers in those websites that I provided you dealing with APA, you'll see that those documents or those writings have abstracts. Well, you're not doing a thesis or a dissertation or even a full research paper. All you're doing is a short 2-page summary. So you don't need an abstract. Your summary is actually an abstract already, because what an abstract does is it gives you a brief synopsis of the actual document. Well, that's what your summary does. So you don't need to write a summary and an abstract, because you would be duplicating the effort. So you only have to do a summary. Okay. So hold on just a moment. Sorry about that. I'm at my mother's and her phone rang just now. So, but anyway, so only write the summary. Do not include an abstract. Okay. It tells you how you should format the paper. You want an ID block in the upper left corner, and that ID block has to be single spaced. The ID block should have your name, my name, the class you're in, Physical Science 1010 section S01, and the date that you submitted to me. You do not need a running header. A running header is useful if you're doing a long paper, but for our purpose, you don't need a running header. All you need is an abbreviated header with your name and the page number in the upper right corner. Okay, so an abbreviated header, all you're gonna put is your name in the abbreviated header, and you're gonna include page numbers. And because you're writing a short paper, you also do not need to use what we call in-text citations. If you've ever done a research paper before, you know that an in-text citation is meant to distinguish sources that you used. So if you're writing a research paper, you might have 5 or 6 different sources that you're utilizing, maybe even more. And it would be proper to, document or cite your source within your actual paper so that anybody reading it knows where the material came from. Well, your summary is only pertaining to one article, the article that you got approved. And in addition, in your very first sentence, you credited the source, so that I know after the first sentence, everything you're writing is in your own words, dealing with the article that you are, summarizing. Okay, you don't have multiple sources. You're not allowed to use Wikipedia or, I get a lot of folks, Britannica Encyclopedia or any other sources The only credible source for this project is the article that you are using, the one you got approved or the one you're using, okay? You do not have multiple sources. So if you don't have multiple sources, you don't need to use in-text citations, okay? The only thing you do need to pay attention to is, number one, that you're writing the summary in your own words, telling me what the article is about. Number two, you're telling me how the article connects to this lecture class. And number three, if you quote material from the article, which you're allowed to do in a limited capacity, then you have to put quotation marks on what you quote. And after you close the quote, put the page number in parentheses telling me what page of the article you took that quoted material from, okay? So those are the rules that you have to follow in doing the summary. 1-inch margins all around, is type double space. You only are writing the summary in your own words and connecting it to the class. You have an ID block in the upper left corner that's single spaced. You don't have a running header. You're using abbreviated header with your name and the page number in the upper right corner. And you do not need to use in-text citations because you only have one source that you named and credited in your very first sentence. And if you're quoting, the material is in quotation marks and you put the page number in parentheses after you close the quote. Are there any questions on that? And I'm taking that directly from the project details. Any questions on that?
So this ID block, is that right before you start writing your paper?
It's in the upper right, upper left corner, right? So before you start actually summarizing, right?
Right. Okay. I was just making sure.
Right. Anybody else? Please ask your questions about what I've covered. Okay, so to help you with that, if you go into the project folder, I'm just gonna back up here. There are some picture templates that I've included, okay? All right, and so here's a picture in that picture template folder, oh, sorry, that shows you the basic structure here, right? See the ID block in the upper left corner, single space, an abbreviated header with your last name and the page number in the upper right corner. That's your header. You're not using a running header. You don't need an abstract. You're using APA for the margins and spacing, and that's 1-inch margin all around, tight double space, except where I indicated that the ID block is single space, and then you are going to give your summary a title, okay? And then you're going to space appropriately and start your first paragraph. And I've given you your first sentence. You do not need to use in-text citations. I remind you of that here on this picture. And then a cover page is optional. I would suggest to you that you not include a cover page and that you just format according to this page that I've shown you here, okay? Any questions about what I've included here on this picture that you can access right from the project folder? Okay, so that gives you some basics to work with in the event you're ready to start your writing. In the coming weeks, we're going to be revisiting the project details, and I will be talking to you about, I'll be covering information on the reference page that you have to include. I'll talk to you, we'll take a look at some of the sample papers, and I'll be pointing out some things for you there as well. And then I'll definitely talk to you about plagiarism and how you can avoid it. And then the last thing I'll do probably a week before your project is due, or close to the, closer to the time you have to submit it, is to cover the actual rubric. Okay. Any questions about that? All right. Now, if you go into the announcements, another thing that I've made available to you is if you scroll, you might have to scroll a bit because I've got quite a few announcements now. There is a class project video. Okay. So you can see here, there's a, if you click on that, you have access to a video that talks about the project. It doesn't talk about finding an article, but it does explain the writing of the summary and the rubric. Okay. So if you forget any of the things I've covered, you can definitely go back to the video, but I'll be covering portions of the, the project details here in class, and you can ask questions in as well. Okay. And it goes without saying, at any point, if you have questions about anything that you need to do regarding this project, please reach out to me. It is better to ask the questions than to assume and make mistakes. Okay. Like I tell students, this project is worth 20% of your grade. So you don't want to be losing points on this because, it is an important assignment, but it is not an unmanageable assignment, because really all I'm asking you to do is, in your own language, tell me as best as you can what the article is about and how it relates to things you've come across or learned in this class. All right? Everybody okay with that? What are your questions on the project? All right. So I'm going to go into today's overview that deals with work and energy. And so you can see from the objectives for today that we'll be looking at conservation of energy. If you recall, last week we talked about conservation of momentum and how that's relevant in collisions. And today we'll talk about the conservation of energy, and we'll see situations where that's appropriate. We'll talk about work and look at how we calculate work. And of course, by now, anytime we're calculating anything, units are going to become critical. And then we'll also talk about, what has to be present in order to do work. What does that mean in the physics world, if you will? How is work different from the everyday use of the word work? We'll look at some different types of energy: kinetic energy, potential energy, and we'll look at how they're connected to work. And we'll look at some situations where there are energy is being exchanged, and talk about what is that? What are those kinds of situations where energy is exchanged? We'll look at how you calculate kinetic and potential energies. Of course, that means we've got to look at some formulas if we're going to do some calculating. And then we'll look at power and what's the connection between power and work and energy. Okay, so those are the kinds of things that you should be able to do as a result of completing this overview. You do have some activities that you need to complete for this week. You have problem set number 9 that's due this Saturday. And remember, problem sets always lag a week behind. So last week we covered momentum. You did a discussion on momentum. And so this week you'll complete the problem set dealing with momentum. You have a discussion that relates to energy, because that is the topic for this week. And so You know, with every discussion, the rule is what you have to first post your answers to the questions, and then you have to respond to the posting of 2 of your classmates. Please make every effort to make your responses engaging. Try to have an honest dialogue or debate with your classmates about what they've posted, and move beyond simple answers like I agree or I like what you posted or we got the same answers. You should be attempting to replicate being in a classroom with your classmates where y'all are working these things out together. And so you're sharing ideas and feedback while you're working. That's exactly what should be happening in the discussion, right? And then there's, of course, reminder of how you turn in your problem sets to me so that you're using the proper formats, and a link to the class questions forum. If you want to share something that, ask a question and have your classmates chime in, feel free to post your question there. Of course, you can always reach out to me with your questions in email, or you can come during an office hours visit. To meet me during office hours, you don't need an appointment, but it would be helpful to know the time you plan on joining in so that I can make sure the room is, prepped, if you will, meaning so that you can have some one-on-one time. Okay? Any questions about any of that? Okay, so let's go into the readings materials and the viewings materials. So there are 2 chapters in your CK12 textbook that deal with work and energy. You are supposed to read those 2 chapters. And then if you have questions about anything you've read in those 2 chapters, please don't hesitate to reach out to me. That's, it's important to get those types of questions answered if you're reading material in the textbook, okay? But, just with anything, we're not gonna read the book here. That's your task, and you should follow up with me if you're having questions. There are some videos that deal with energy that you should watch. And after watching those videos, if you have questions, please don't hesitate to reach out to me with your questions, okay? Everybody clear on that? All right, so the last item there, let me just clarify for you, because I had a student reach out to me asking about the acknowledgements. Why are those acknowledgements there? I thought I explained this in week number 1, but I'll explain it again just to be on the safe side. The acknowledgements are my bibliography. So just like I want you to be, honest and give credit to your sources for the project that you're doing, I also have to be, proper and give acknowledgement to the sources that I use. So for every overview, I acknowledge the sources that I use to put this material together. And so that's like my bibliography, right? You can take a look at it to see, if you want to officially make note of some of the sources that I use, but it's really intended to let the world know that I am giving proper credit and that this material is not my own. So that's why the acknowledgements are there, okay? So if you see that, it's not something that you're supposed to be working on. It's just the bibliography for that particular overview, okay? All right, so what I'm gonna do now is go into the supplemental notes on energy and work, because those are my lecture notes. And when I say my lecture notes, I don't mean I created them. I mean, they're the notes that I'm using to cover this material. They actually belong to Entellus, but since they're open, that's what Creative Commons means. Since they're open, I can use them as long as I acknowledge my source. And there it is, see? So at every turn, I make sure that I don't plagiarize. All right. And also in every note packet, I always include this information on how to study, because I want you to be fluent in knowing how to successfully complete this material. All right. So in this particular packet, we're going to look at the law of conservation of energy. We'll talk about work, and then we'll look at some of the various types of energy. After I've covered this packet, there are a couple of simulators that I want to show you. And then I'm going to take you out to another website, and we'll take a look at some scenarios where the law of conservation of energy is relevant. So, work and energy in everyday life. So, of course, we use those terms in conversation. You know, I might ask you, hey, did you have to go to work today? Or, you know, I might make a statement about energy, you know, man, you know, those high energy, those energy drinks really have a lot of calories. That's how we might use those terms in casual or everyday conversation. But we have to be very careful when we are using them in the physics sense of the word. Okay. And so while, you know, in everyday conversation, we don't have to worry about being as precise in our language. When we move to the physics definition of the words work and energy, we have to be careful because they are very rigorous in nature, meaning they depend on certain properties. Certain properties have to be in place and certain conditions have to be met to do work and have energy in the physics sense, not in the everyday sense. Okay. And so, you know, our understanding of those terms is based on, you know, experiments that have been done. And so through these experiments, you know, we understand now, we know now that energy is something that can be exchanged. That this work and energy and different forms of energy are interchangeable. And so, you know, that is a monumental achievement in the world of physics, if you will, because it really does give us some insight as to how our actual environment works. Energy is one of those properties that you often you can't directly see it, but you know that something is happening because of the way systems get changed and how the objects are impacted. And so the fact that we're able to figure out that energy is being transformed from one form to another is pretty important, given it's not a property that you can readily see and you know, you measure it in many instances by looking at the impact or the change that it creates. So one of those things that we can measure is work, and that is directly related to energy, because in physics, remember, we're talking about the physics definition, not I go to work from 8 to 5. We're talking about the physics definition of the work, where energy has to be transferred. So when you're doing work in the physics sense, you have a transfer of energy that causes an object to be displaced by a force. So you have to do work, there has to be energy transferred, and you have a force that causes an object to be displaced. So you apply a force to an object, that object gets displaced. That's another word for saying what? It moves. And so we know that work is being done. Okay. Furthermore, whenever work is done, energy is exchanged or transferred. So you see, that's very different from how we might be using work in the everyday conversation. We use the letter W to denote work. Please be careful. Do not mix up this W for work with the W for weight. They are very different properties, but they're using the same symbol. That's why it's important that you be able to distinguish the circumstance under which you're operating or the problem that you're trying to solve, so that you use the appropriate symbols and you use them in the right context, okay? The way we calculate work, it is the product of force and displacement. So you multiply force times displacement to get work. But you have to be very careful, okay? Whenever you're multiplying force times displacement, you have to make sure that the force and the displacement are in the same direction. See, there's a stipulation, right? Whenever you're multiplying force and displacement, they have to be in the same direction in order to do work, okay? So imagine pushing an object across the floor. Let's say you have a box and you push that box across the floor. You're exerting a force on that block. That block is moving in the same direction that you're pushing. Work is being done, okay? So you might ask the question, well, are there circumstances where you aren't doing work? You could have a force, but nothing moves. For example, let's say I push on a wall. I'm exerting a force, but because there is no displacement, the wall isn't moving, then I'm not doing any work. Or of course, if I don't apply a force, there's no work, okay? Now, there is a scenario where you will have a force and you will have a displacement, but no work gets done. I think it's pretty easy to see if the force is 0 or the displacement is 0, then you don't have any work. But what about a scenario where there is a force, there is a displacement, but work is not done? Well, the definition says what? If they're not in the same direction, then there's no work. What kind of scenario would that be, where you have a force, you have a displacement, but they're not in the same direction? So no work gets done. If you carry an object, then your force is supporting the weight of the object. But if you're carrying the object, you're walking forward. So you walk forward, you hold the object and carry it, there's no work being done, because the force and the displacement in that situation are perpendicular, okay? So in the situation where you carry an object, the force is supporting the weight of the object. That's vertical. If you're walking forward, that's horizontal. So your force is pointing vertically, your displacement is pointing horizontally. They're perpendicular to each other, so no work gets done, okay? So that's a kind of a unique situation. In many instances, the force and the displacement will be along the same line, and so work will be done. But if you carry an object, that is not the case. So, because we are using force and displacement, we have to look at the units that are involved. We know that the unit for force is the Newton, and we know that the unit for displacement is meters. And we're talking about SI units, right? We work in the metric system or the SI system. So the unit for force is the Newton. The unit for displacement is the meter. When I put them together, when I multiply them together, I get a Newton meter that is equivalent to a joule. So 1 joule is equal to 1 Newton meter, okay? So when I take a Newton I multiply times a meter, I get a joule. Okay, so it's important that you know that so that you use the units correctly. And we'll take a look at a couple of examples in problem solving where that becomes important. The work energy theorem. So the work energy theorem looks at the relationship between work and energy. Okay, because we already said that work, it involves a transfer of energy. So what's the relationship there? The net amount of work done, and they use this W with the net subscript to distinguish, just like we did the net force. Now we're looking at the net work. So the net work done on an object or system changes its kinetic energy. Okay. Now, here's that word again, kinetic energy. So we have to see, how do we determine the amount of kinetic energy? All right. So let's look at this formula that expresses the work energy theorem. All right. So you see here, in order to do work, we're looking at what? The difference between the final kinetic energy and the starting kinetic energy, where kinetic energy is defined as 1/2 mass times velocity squared. Kinetic energy, KE, we often use the symbol KE. KE, kinetic energy, is equal to 1/2 mass times velocity squared. And if we look at the difference between the final kinetic energy and the starting kinetic energy, that tells us how much work is done. Because if work is done, the speed of the object is going to change. Okay? So if we look at the difference between the final kinetic energy and the starting kinetic energy, that tells us how much work is done, that work net. Okay? And that is what we call the work energy theorem. Last week, we looked at something called the momentum, the impulse momentum theorem. This week, we're looking at the work energy theorem. Okay? Gravitational potential energy. So anytime that work is done on an object against gravity, think about it. Gravity points down. If we're doing work against gravity, it means we're doing work pointing up. Anytime we do that, there's energy that gets stored. And that stored energy is called gravitational potential energy. So to lift an object against gravity, we store up energy called gravitational potential energy. I like to call gravitational potential energy by virtue of position, because as an object's height changes, it stores up or releases gravitational potential energy. Whereas kinetic energy is often referred to as energy of motion, because you look at how the velocity changes. Gravitational potential energy looks at how the position or height of the object changes. Okay, and that's what you see in the formula, that if an object is lifted to a certain height h, it gains gravitational potential energy relative to the, in our case, relative to the earth. How do we figure out how much gain? We call that delta PE. Delta means what? The change in potential energy. How much potential energy is gained as we increase the object's height? That amount is mass times gravity times height. So stored energy by virtue of position. Okay? So they give you a picture here, the storing and releasing of potential energy. Okay? So you can see, and let me just scroll and bring the picture more into view. There we go. Sorry, I'm trying to balance that with the screen sharing. Let's see if I can move that. There we go. Okay. So they're showing you here an example of a clock. So this clock is like a grandfather clock that has a bob hanging on a chain of some sort. And so if you exert a force on the chain, so you see that like on that chain, there's like a little ring, a little circular ring at the bottom. Let's say you put your finger in the ring and you pull down on that chain. So you exert a force downward, that's the red arrow F, and that chain undergoes a displacement D. And notice they're both in the same direction. F and D are in the same direction. And as you pull and move that chain through a displacement D, the bob, that's the little, almost looks like some type of, to me, it almost looks like it's an acorn shape, but anyway, it's a bob that's hanging at the end of the chain. And as you pull a chain down through a displacement D, the bob goes up through the same displacement D. But notice the directions, right? The size of that displacement is the same, all right? And that displacement has a size H, the height that it moves, H. So we know that the force applied is the weight of the bob, mg, and the distance that it moves is h. So the work done is mgh. And let's say you pull that chain and move the bob up a certain height. If you release the chain, the bob falls through the same height, h. So by pulling the chain down, you store up energy that is equal to the work that's being done. And when you let go of the chain, the energy that's released is equal to the amount that you stored up. Okay? So you see there's this kind of exchange in energy going on. You pull a chain and store up potential energy, you let it go, and you release that energy. Okay? So if you understand that idea of storing up and releasing energy, that can bring us to a point where we can talk about the idea of conservative forces. You notice in the picture with the clock, we had to exert a force, F, to move the chain. And so the question becomes then, if you're exerting these forces on objects, under which situations will energy be conserved? Well, the only time that you will have energy being conserved is if the forces that are being exerted are conservative forces. Well, how do we know if a force is conservative? It says here, a conservative force is one for which work depends only on the start and end points and not the path taken. So it doesn't matter how we get from start to finish. Doesn't matter the path that we follow. The only thing that matters is where we start and where we stop. And so an example of a conservative force is gravity. So if you do work against gravity, that force is a conservative force. And so the work that's going to be done does not depend on the path taken. Okay? When we are exerting a conservative force like gravity, the mechanical energy is conserved. So when we do work with a conservative force like gravity, mechanical energy is conserved. What is mechanical energy? The sum of kinetic and potential energy. Okay? And so when you have conservative forces acting on a system, the total mechanical energy is constant. Just like we learned last week that when you are dealing with an isolated system, momentum is conserved. When you are dealing with the system impacted by conservative forces only, mechanical energy is conserved. Okay? So the total mechanical energy is constant. So the kinetic energy plus the potential energy will always give you the same total. If you look at the system at any point, the total mechanical energy is fixed. So there we go. Here we're looking at the idea of expressing the mechanical energy in terms of the initial mechanical energy and the final mechanical energy. And what we have is it broken down. The starting kinetic energy plus the starting potential energy will always give you the same total as the final kinetic energy plus the final potential energy. Why? Because the total amount available is fixed. Why is it fixed? Because mechanical energy is conserved. Why is the mechanical energy conserved? Because you're dealing with conservative forces only, like gravity. And anytime gravity is doing work, you're going to have a conservative system. Well, what about systems where energy is not conserved? What about systems where you're dealing with non-conservative forces like friction? So a non-conservative force is one for which work depends on the path. Okay, so how you get from start to finish matters when you're dealing with non-conservative forces like friction, okay? And so they give you an example here of this baseball player that's sliding, and there's a friction force being exerted on the player. Notice that the player's displacement is to the left, but the friction force is to the right. So in this case, you're going to have, heat being generated, right? As the player slides, they're going to be exerting, there's a friction between them and the surface or the ground that they're sliding on, and that will generate heat. So some of the kinetic energy of the player is going to be converted into thermal energy, okay? Well, if the kinetic energy, part of the kinetic energy is converted into thermal energy, then that means some of the energy in the system is going to be lost, because friction is what we call a dissipative force, meaning you generate heat and that heat energy is lost to the system. So energy won't be conserved, okay? So anytime you deal with friction, you're dealing with a non-conservative system, and so energy is going to be lost, all right? So now what we have to talk about is, how do we determine the work done by this friction force? How do we determine the work done by a non-conservative force like friction? Well, what we look at is we have to take our conservation of energy formula and we have to add in the work done by this non-conservative force. So you see on the left-hand side of the equation, we have to modify it and add in the work done by a non-conservative force. The work done by the non-conservative force is designated as W with NC as the subscript. Work non-conservative force, okay? So now, our starting kinetic energy plus our starting potential energy plus the work done by any non-conservative forces equals to the final kinetic energy plus the final potential energy. You can see that in this expression, if we rearrange it and solve for WNC, means we have to take everything that's on the left side and move it to the right side and leave WNC by itself. So subtract out KE initial, subtract out PE initial. On the right side, you will then get the work non-conservative is equal to delta KE plus delta PE. So the change in our kinetic energy plus the change in our potential energy is equal to the work done by our non-conservative forces. Okay. Now, we can then expand the law of conservation of energy to look at energy besides just mechanical energy. Mechanical energy is conserved when you're dealing with a conservative force like gravity. But if you want to look broadly at energy conservation, the law of conservation of energy, it says that the total energy is constant in any process. And so what you have to do is you have to take all of your different types of energy that you start off with and add them up, and then look at all the different types of energy that you end with. When you add them together, right, the total on the right side has to always be equal to the total on the left side. So the energy that you start with has to always be equal to the energy that you end with when you're looking at the conservation of energy in a broader sense. Okay, so it says what? Energy can change form, but the total amount always remains the same. In fact, that's typically how we express the law of conservation of energy. Energy cannot be created or destroyed. It can only change forms. Okay. So it says here in this equation, we see kinetic energy, potential energy, work done by non-conservative forces, and then OE. That represents any other form of energy. Could be electrical, could be chemical, radiant, nuclear, thermal, any other form of energy. So we take all of the different types of energies, add them up, and then we look at all the different types of energies that we finish with. The total has to remain fixed. Efficiency. So what we want to do when we deal with efficiency is look at how useful the work that we get out of a system will be compared to the energy that we put in. All right. So so even when we're dealing with a system, a situation where you have energy being converted from one form to the another, what sometimes we want to know is how efficient is that energy conversion process? Well, in that case, what we have to do is we have to look at, well, how much work do we get out for the energy that we have to put in? Sometimes you might hear that kind of like, how much bang for our buck do we get, right? We put in all this ton of energy. How much work are we able to get out of that system as a result? Okay, so the ratio of work out to energy in. And if we're looking at real world processes, the work that you get out is always going to be less than the energy that you put in. There is no 100% efficient process. So that ratio is always going to be less than 1. And so many times you see that efficiency expressed in terms of a percentage. Here's a table that shows you the efficiency of some real world types of processes. When I finish here tonight, I don't know if it shows that on there. I'm going to go walking. Okay. But even if I was doing like a lot of times what they consider like a more rigorous type of exercise, like swimming or climbing. Look at their swimming is only a 2% efficient process, like if you see Olympic swimmers swimming, you know, like backstroke or breaststroke moves in the swimming pool, 2% efficient. It's a little bit better underwater, not much more, not much better. Look at the efficiency of a gasoline engine versus an electric engine or electric motor. Electric motors are 98% efficient. That's why we want to move to electric cars as opposed to gasoline car, you know, powered cars. Okay. So that takes us to power. So if efficiency looks at how well we utilize energy, the power looks at the rate at which we use energy. And so it's looking at the rate at which work is being done. Now you have to remember that work and energy are interchangeable, right? So when we're looking at the power of a system, we're looking at, you know, the work that's being done per unit time, okay? And the unit in the metric system for power is the watt. So 1 watt of power is equal to 1 joule of energy per second. Okay. So work per unit time, joules per second. Joules per second is equal to watts. Notice again, we're using a W, but this time the W is a unit. Okay. So work over time, that gives us power. In the English system, this might be a unit that you've heard or have some familiarity with, horsepower. A lot of times they measure, you know, like muscle cars in terms of their power rating is the horsepower, or like a Hemi engine. We'll talk about horsepower. Okay. 1 horsepower is equal to 746 watts. That's your conversion factor. Okay. Power, work per unit time. And look at, they give you a chart here that shows some energy conversion processes within humans. Okay. So this talks about the rate at which the body uses food. That's called a metabolic rate. You know, you hear people say that some folk have a high metabolism or a low metabolism, or the metabolism is off, right? That is talking about how the human body uses food, because we know that food is our source of energy, right? We need energy to be able to sustain ourselves. And so how efficient, or if you will, at what rate does the human body utilize energy? Metabolic rate. So you see that if you were looking at power when the human body is at rest, you can see that the liver and the spleen have, you know, a higher metabolic rate than some of the other organs in the body. And some of that has to do with the fact that, you know, the liver and the pancreas and some of those organs are directly involved with enzymes that help with digestion. This is an interesting chart. So they do some projected energy use for worldwide. So you can see here, you know, our energy consumption right about now is right at about 654 times 10 to the 18 joules you know, on planet Earth, if you will. Okay. And you can see that progressively the world's energy consumption has gone up. And by 2035, which is, you know, seems like a far away, but it's not as far as we might think. You know, we're going to be right about 812 times 10 to the 18 joules of energy worldwide. And you have to think about how big a number that actually is. You know, times 10 to the 18, it might not sink in immediately, but think about that if you had to write that out with all the various zeros. That's an extreme number. And then this one breaks down power consumption by different countries. And it's, you know, they're talking about per capita here. And that term shouldn't be unfamiliar to you because, you know, here in the past 2 years, that idea of per capita has become very important as they talk about COVID statistics and what have you, right? So this idea is looking at various nations in the world and, you know, their power consumption compared to their wealth. So they're looking at GDP. That, you know, that's an economic term that tells you something about the gross domestic product of a country, and then kilowatts per capita, right? So US is right up there. Japan's beating us just a bit. I'm not sure when this graph was made, but it gives you a relative idea that we're near the top. I would, you know, I would kind of bet that maybe China is moved up in stats since this was produced. And so, you know, that says something about, you know, the more money you have in a country, you know, the more power you're using. You know, in other words, you're responsible for a lot of the energy use that's taking place worldwide. Right? So that's what I wanted to share with you in this packet. What I want to do now is I'm going to go into useful links. Well, actually, before I do that, let me go into the announcements and bring up our extra notes. So I'm going to go and find that link to that. Let's see. Extra resources, there it is. And I'll go into this folder and I'll bring up the one for energy. And this kind of shows you how to break down of units. You know, for work, you're using Newton meters and you get a joule. And then I show here the formula for potential energy, the formula for kinetic energy, and I break the units down for you and show you how each of them winds up being a Newton meter, which is a joule. So we can see that there's a direct relationship between work and energy because they're using the same units. They're interchangeable, right? And then you have this packet here, which I like, that kind of talks about, you know, the various forms of energy, okay? Gives you the formula for kinetic energy, the formula for potential energy, the formula for work, okay? And then we get to some examples. That's where I want to go. So it says here, Brett's backpack weighs 30 newtons. How much work is done on the backpack when he lifts it 1.5 meters from the floor to his back? So you can almost visualize this. Brett lifts the backpack up. The backpack moves up. So they're in the same direction. The force and the distance are in the same direction. So we multiply. 30 newtons times 1.5 meters gives us 45 joules. Notice I've taken the work formula and put it in the pyramid. W is on the top. So since I'm solving for W, I multiply F and D together because they're right next to each other. Here's another example. And I like this one because it gets into that whole idea of force and distance being in the same direction. It says a dancer lifts a 40-kilogram ballerina 1.4 meters in the air and walks forward 2.2 meters. How much work is done on the ballerina during and after the lift? So we have the mass involved for the ballerina. We have the distance during the lift and the distance that they walk forward after the lift. And so they want us to find the work being done in each instance. Okay. Now, be careful here, because a common mistake is that students will take the 40 kilograms as your force. 40 kilograms is not the force. 40 kilograms is mass. To get the force, you have to multiply the ballerina's mass times the acceleration due to gravity. Why? Because that gives you the ballerina's weight. If you're going to lift the ballerina, you have to support the ballerina's weight. Well, how far did you move the ballerina's weight during the lift? 1.4 meters. Multiply that together, you get 549 joules. If you tell me 549 Newton meters, I'm going to take points because you did not properly give me the unit joules. What about after you lift and walk forward 2.2 meters? Well, here's the classic example of carrying the ballerina as you walk forward. And so the force is pointing vertical as you support the ballerina's weight, but the motion is actually forward, so they're perpendicular and not in the same direction. The force and the displacement are not in the same direction. They're perpendicular to one another, so no work is done. Any questions about either of those examples that I've worked? Okay, so let's take a quick peek at the law of conservation of energy. So energy can change forms, but it cannot be created or destroyed. And they say under ordinary conditions, they mean there where you don't have any friction involved. And so you can have, they mean where you can look at the system in an isolated capacity, my bad, okay? So examples of energy transformations, you can take potential energy and convert it to kinetic energy. You can take mechanical energy, which is kinetic or potential, or kinetic and potential, and convert it to thermal, which is heat. And then, for example, you could have chemical energy that gets converted into thermal energy. As a chemical reaction takes place, it gives off heat, for example. So you have some scenarios where we can look at the conservation of energy. These are systems where gravity is the main source for your force, okay? And when you are dealing with systems that are gravity driven or gravity only, you have mechanical energy being conserved, meaning what? You can take your potential energy and convert it to kinetic energy and vice versa, but you cannot gain any additional energy in the system. And this roller coaster example is one where if it's a gravity-driven system and you can ignore friction, or you have to ignore friction, then no matter how the car moves in the roller coaster at any point along its motion, the total energy is going to remain fixed. So when you take into account friction, then you are going to have a system where energy is not conserved. So on the left, you have the marble in the bowl with no friction. In that situation, the marble is going to go back and forth. You know, once it's released, it'll go back and forth in the bowl, always rising to the same height, same maximum height. Whereas when you include friction and you release the marble, eventually all of the energy is going to be released or lost in the system due to heat, and the marble will eventually settle in the bottom of the bowl, because at every part of the motion, energy will be released or lost in the system, slowing the marble down and making it go lower and lower in terms of its height. And that's what's being depicted here as well with the skier. So you notice on the bottom of the picture, they say unpacked snow. So that unpacked snow is going to provide friction and slow the skater down once they get to the skier, the skier down once they get to the bottom of the slope. If you take that snow and pack it so that it's slick like ice, you're going to have less friction. And so the skier is not going to slow down as much when they get to the bottom of the slope, and meaning they will not lose all of their velocity in that particular scenario. And then power, as I mentioned before, power is the rate at which work is done. So it's work divided by time. And the unit of power in the SI or metric system is the watt, which breaks down to 1 joule per 1 second. All right. So the only other thing that I want to do, the last thing that I'll do, is to go under useful links. And I'm going to go into the simulators link, because I want to take you out here to this website. I'm not sure if any of you played around with this website and tried some of the simulators that they have out there. But here is a simulator that we looked at some time ago when we dealt with projectiles. And so I'm gonna change this to a 0, and I'll change this to 65, because that gives me a much better visual, okay? And this time I'm going to look at energy. So notice that you have kinetic energy and potential energy. This object is starting from the ground, so it has 0 height. So it has 0 potential energy, but it's starting with an initial speed of 5 meters per second. So it has some initial kinetic energy. So let me start it. And what you can see is that at any point along the motion, the kinetic and the potential energy always give you the same total. Sometimes you have more potential energy than kinetic. As the object rises, its height gets bigger, the potential energy will increase. It's storing up more energy. But notice as it gets higher and higher, it'll reach the peak where the vertical velocity is 0, and it'll have the smallest value of kinetic energy. Once it goes past the peak, it starts to fall. So the potential energy is going to decrease while the kinetic energy increases, but the total amount is always the same. Why? Well, this projectile operates under the control of gravity only. Remember, a projectile has no horizontal acceleration, and its vertical acceleration is due to gravity. So since this is a gravity-driven system, it is going to conserve mechanical energy, meaning the total energy in your system is fixed, okay? Another example of a gravity-driven system is a simple pendulum. So we'll run it in slow motion, but pay attention to the energy only. Notice that the total amount of energy stays the same, but look what's happening. As the kinetic energy is increasing, the potential energy decreases, but the total is always the same. Now, the potential energy is increasing and the kinetic energy is decreasing, but the total is all the same. Why? Because energy can change forms, but in this situation, cannot be created or destroyed, and it's being controlled by gravity. Okay? So we can see here, if I take that off, you can see the exchange of energy, the transfer of energy, but the total is fixed because gravity is a conservative force and this is a conservative system. Okay. All right. So those are just some examples of some systems where energy, mechanical energy is conserved. All right. And I just clicked on, I went to useful links, clicked on simulators, and I tried out the projectile because we had looked at that system before. And I looked at the pendulum because that's another example of a gravity-driven system. All right. So I'm stopping the share. I do apologize. My video is not the greatest right now. But what I want to find out is, what are your questions about anything I've covered tonight? Don't hesitate. Just unmute and ask or type it in the chat. Sorry, I muted myself. If you don't have any questions for me, I'm done with my portion. While you're working this week, don't hesitate to reach out to me if you do come across something that you have a question about. Other than that, I'm going to stop the recording. This recording